Welcome back, everyone. And now we will get into the topic of autoencoders. If you recall, we did so far feed-forward networks, right? Dense nets. Right? The dense nets were or feed-forward layer were, and like all of these and everything in between. Are we together, guys? Right? Everything connected in layer 1 to layer 2. Every node, every neuron in layer 1, LN1, connected to every neuron in layer L2. Isn't it? This was your feed forward. What we would do is, and just to very quick recap, every neuron is a Z and an activation. Z is the linear transform, W dot X plus B, isn't it? For every neuron, whatever the inputs are coming, X1, Xn, right? And then you have the weights, W1 to Wn, and this is the bias coming in. So Z is this, and this is the activation. The output is activation of Z. Right? This is what a neuron is. This is what a dense layer is. The second thing we learned so far is that the other approach, the other thing that we can do is convolutional neural nets. A convolutional layer is made up of filters. Like you give it an input, and from this you apply filters, filters. These are also called kernels. The old term used to be kernels, followed by activation, followed by pulling, isn't it? So this together is one connet layer that would produce feature maps. Feature maps across so many channels. We also learned, so these are the two architectures that we know so far, isn't it? Now we also know, and look at this. Can I do this? I can take layer 1 with, let's say, a large number of layers. Suppose the input is, I'll take an example. I have input coming to these layers. Suppose I have 100 neurons. Are we together? And suppose I create, just for fun, I can create a second layer which is much smaller. I can do that. Let's say I can create a second layer of 2. L1 has 100. L2 has, and this is neuron. Right? And this is neuron. And then again, it is a dense connection. So how many weights will I have in between?
100 times 10.
Yeah, 100 times 10. Number of weights. And then biases. There'll be 10 biases plus 10 bias terms. Weights, bias. Weights and biases, right? Before it produces this 10 output. Well, remember that when you were building your convolution, your simple feed-forward network, you had a choice. You could choose how many layers you would give, right? Now, suppose, just for fun, I'll ask you this question. Can I take the third layer now and this again, I can make it to be L3 is equal to 100, up the number of neurons. Is there anything that prevents me from doing that? Nothing, right? Now, you say, well, this looks funny. I decreased, I went down to low number of neurons, and then I went back to high number of neurons. I can do that.
So, Asif, so the third layer, the
Yeah.
100 neurons, right? So then there will be 100 biases.
Yeah. So in this case, it will be like, so this has 10 cross 100 plus 100 biases, right?
Okay.
100 weights. That is correct. That's very good, Krishna. Biases.
The L1 also will have 100 biases, right?
L1 also has 100 biases. So see, L1 is getting its weight from X1, X2, Xn, right? And it is getting its weight, whatever it is, the inputs, it is getting the input. So it will have the same thing, like whatever the number of inputs are, right? And it is doing that. But let us say, let me just say, what if, right? This is, I get an input, which itself is 100. I treat this as an input layer. Yeah. So in which case there is no cross connection. There is just input going directly into the neuron, right? Each of the neurons. And the only the real network is this layer. And you're basically saying that I'm going to decode this. I'm going to blow it up again to this representation, 100. And I ask this question. So this is input. And I will ask this question. Let's stare at it and what can we do? First of all, what kind of network can do that? A feed-forward network can surely do that, right? We also learned about convolution and deconvolution. CNNs can also do that, isn't it? So the two architectures that we know, feed-forward and CNNs, you can use both to build something like this. And now the question is, this looks beautiful. Looks like a nice dumbbell. What in the world can we do with this? Suppose we did this. So suppose the output that came out of this, right? It is again some output, right? Let me just call it X prime. X prime will be made up of X1 prime all the way to Xn prime. It will be this vector, isn't it? It is basically the output. This one will be Xn prime. This one will be X1 prime. Does this make sense, guys? Right? The output of that. Now, you know that somehow this is much smaller. This is only a 10. X belongs to a 100-dimensional space. Does it make sense, guys? X belongs to a 100-dimensional space. This thing, what comes out here, what is coming out here, let's call it Z vector. Z is the output of layer 2 here. Z belongs to, what is the space it belongs to?
Yeah.
A 10-dimensional Euclidean space. So observe something very funny. We are taking some information, an array, which belongs to 100-dimensional space, array of 100 numbers, and we are producing an array of only 10. And then we are blowing it up to an array of 100. Somehow, when you bring it down to 10, it feels as though we'll lose something, right? Isn't it, guys? We are losing something, it seems.
Yeah.
Right. So it's something like you have a 3-dimensional object, a sphere, and you bring it to 2-dimension, it begins to look like a circle, a solid disk, right? But hey, you project a light on top of it, on the ground, it will show up as a disk, isn't it? But if I try to invert the disk, how do you know it was a sphere? It could have been a what is those American football thing called? That funny shaped.
Elliptical.
This kind of thing. But this also would project on the plane. What will it project? It will also project a perfect circle, isn't it? So a circle disk can invert itself. It could have come from a sphere. It could have come from this. Do you see? Logically, mathematically, one would say, wait a minute. Wait a minute. I cannot just take simple projections, because if I take simple projections, it's not going to work. Right? And yet, it looks beautiful, isn't it? And suppose we say, what if, we don't know why or how, but what if x prime is x? We get back x. That it comes up with a representation of the data in such a way, it doesn't do a direct projection, but it has some clever trick to remember what the original shape was. Are you getting the intuition? It has some way to remember what the original shape could have been, right? And what if x prime is this, right? Somehow. Suppose you could do that, right? So now think about what use is it? Because you guys have all been asking me this question. What use is it? So I will let you guys answer this question. So this is it. This is your one layer. This is it, right? And then this produces back the original layer. I'm just writing it in this way, right? Input, output, x prime comes out, right? What use is this?
Data transmission. You transmit
Come
data. Data transmission. You can reduce it, transmit.
See, guys, suppose I have to transmit an array of 100 numbers.
Compression.
But this is a much more compressed representation.
Data compression.
Isn't it? It's a compressed representation. That is one use of it. Right? Am I making sense? Yeah. So just hold this idea. It is only one of the uses. If I could do that, instead of transmitting X, what could I have transmitted? I could have transmitted Z over the pipeline. Right? So in real life, does it happen, guys? See, when you and I are talking, right? And some in the code, you see the stenograph, they're taking little notes, right? Quickly typing in furiously, shorthand notes or something like that, or whatever you said. Right? Are they capturing all your waveforms and data, your voice, your intonation, everything? They're not, but they're capturing the essence of what you said, the words, and they're capturing the words, and they can repeat the words that you said. Right? So the amount of the space required to store just some strings, some words, is much less than storing the whole waveform, isn't it? And let us say that at the other end, I had some way to speak like you. I just need to know what words you spoke. The job would be done. Right? So these are practical uses that you can do data compression. Now, there is something that, though, you ask yourself, okay, wait a minute. What about the fact that what have I lost in the process? Obviously, it looks a little bit lossy or suspicious that I lose something, right? And the question is, do I lose it? And we will do a little experiment to figure that out. But before we do that, we also notice that, see, suppose I take a picture of a, what should I take a picture of? Let's say I take a picture of a cup or a glass of water. Here's a picture of a glass of water. Are we together? And then I take another picture of a pitcher of water. I could do something called content blending, I could say, hey, and in Photoshop and other things, you can do something like that. You could say, okay, what would be an in-between situation like this? Maybe in-between situation could be, it would look like a little bit like a glass, a pinched glass, but it would still have a handle in it. You see that? You can talk about in-between stages to go from one input, like X to Y, from XA to XB. Are we together, guys? Because the inputs have semantic meaning. We know how to have a little bit of this and a little bit of that, and what it would look like. Right? I mean, you can literally take a pencil and come up with an in-between stage. But sometimes it's possible, and sometimes it's not necessarily possible. So, what about this in this representation? One of the things we would like to have, a desirable property, is that if I take XA goes to ZA and I take XB goes to ZB, right? I should be able to create all the in-between stages, right? Z, let me say K, is a little bit of ZA plus the rest of ZB. So for example, this could be 0.3, and therefore this will be 0.7 of ZB, right? Because see, think about it this way. This is basic vector. ZA is here, ZB is here, right? What is ZK? ZK is somewhere here. Let's say it is 0.3 of ZA and 0.7 of ZB. So it is more like here. ZK is here in the line connecting ZA and ZB. Does it make sense, guys? This is ZK, right? It's a little bit of ZA and a little bit of ZB. You can choose how much of each. If you make alpha is equal to 0, it will become ZB. If you make alpha is equal to 1, it will become ZA, isn't it? So what we would like to have is that in the latent space, so this space, the word people use is latent or hidden. Latent is simply the Latin of hidden, right? Hidden state, hidden world, because you don't see it. What you see is the real world. You see an actual picture or actual number. But this machine, if you could produce a machine like this, it would come up with its own representation. If you also insist that it is mostly lossless, right? That it is able to reconstruct X prime that comes out is pretty much X. Then what does this machine have to do? It will have to somehow, in only 10 numbers, capture everything that X contains in 100 numbers. Does that make sense, guys? Somehow it needs to be able to do that. Now, mathematically, nothing stops it from doing that. It should be able to do that. The only question is how, right? So, but let's look at this. What you call is this part. This part is the encoder. It encodes it into Z, right? And you say that this part is the decoder because it decodes it back into, right? It decodes it back into an output. Right? These are encoder-decoder architectures. Now, you say that, how will we do this? How will we train a machine to do it? Right? So here's a game we can play. You take, at this moment, I won't bring in CNN, though for picture, CNN makes more sense. So imagine that you have flattened the picture. Right? You take, and by the way, one very good example that this book gives, you have deep learning, a visual approach, and I'll take the example from this book. It's a beautiful example it gives to illustrate this point. It says, take a picture of a tiger, right? So how does a tiger look? Okay.
So, Asif, that the latent transformation, right? So that is same as what we discuss in attention all you need.
See, whenever the word latent is very broad,
Okay.
latent simply means that it is not something that is empirically evident or seen. So whatever the machine is internally producing, the vectors that it is internally producing is not visible to you. What is visible to you are the inputs and outputs.
Yeah.
So the word latent, therefore, is very general, and it stands for any vector that the machine is internally producing. And therefore, yes, it is there in attention, it's there everywhere. Those latents are there everywhere, right? And in this case also, right, if I'm giving an input and I'm getting an output, what do I see? I see the input and the output. But this Z is my latent. Please mute yourself. Okay. I hope that makes the meaning of latents clear. Right? Anything that you can't see, that is internal, that's there, right, is your latent. So let's take this very angry tiger and flatten this image into, let's say, 768 pixels. Each pixel is a floating point value. Imagine grayscale. Right? Forget RGB channel or something like that. So now, or you want your RGB channel, you can keep it. What you do is you compress it down to only, let us say 20. Because I'm taking the same number that your book took, so that when you review it, it makes sense. A 20-dimensional space, right? You go down to 20, and then you do this. How would you train this network, by the way? You have this picture. What do? You need a loss function to train it, right? So what do? You have this vector, which is x is equal to 768, belonging to 768 dimensions. 764, I believe, sorry. 764, 28 by 28. Yeah. Yeah, right. Or 784. 780. Yeah, 784. 84 dimension. So now, let's think through it. This goes in, x prime comes out. What do we want? X prime to be the same as x. So would you agree that a good loss function could be, just look at the difference between the two, right? For each of the pixels, and square it. This is your sum over all of these pixels values. This is your total loss. Am I making sense? Well, I just computed the loss, and therefore, can I do the gradient of the loss with respect to the weights? Let's do one thing. Let's treat this function as f. This x goes in. So let's say that this is the f of x. Right? Z, let's write some notation of x of x, and x prime is equal to g, decoder function of z. Right? So f is the encoder function, g is the decoder function. Or if you want, you use E and D, encoder, decoder. We don't use the word E because E in machine learning stands for expectation value, and it can get confusing. Or it stands for error. E is used all over the place. So let's not use E. Let's use F and G. Make sense? So far, are we together, guys? Right? So what we can do, I can find the gradient with respect to all the weights, and so I can train the weights, and soon, and do gradient descent, backprop, everything. Remember all my 4 steps of learning. Forward direction to produce x prime, compute the loss, compute the gradient and backprop it everywhere, and then take a step of learning. And I can go doing it. And what I can do, now the whole question is, I just work with one image. Right? I keep giving the image over and over and over again. Right? Run quite a few iterations of this. Ultimately, what I will notice is that this machine is producing a pretty good picture, because I take this picture and then I deflatten it back into 28 by 28. It begins to look like my tiger. Are we together? Now, so first of all, you realize in principle it can be done. In practice also it can be done. It's very easy. So now the question is, what happened? Right? This machine has somehow learned to produce the perfect tiger.
As if one question, typically what happens to the biases?
Biases are just parameters, right? They also learn. You update biases by taking bias gradient with respect to the bias. So weights and biases are, when we say weights, we mean both weights and biases. Right?
Okay.
That's why people often use the word theta, where theta is either weight or bias. Yeah. You'll often see that the formal definition of will be theta minus alpha, gradient with respect to theta of the loss, where theta could be either the weight or the bias. Right? Any one of the weight or bias. Weights or biases. So are we together here? Now, the way to think about it is that, what has the machine learned? Has it really learned compression? That's the main question, right? Has it learned to compress the tiger? So you can do an interesting experiment. First of all, if it did that, it would be remarkable, right? So what you can do is, you trained it, remember, you trained the entire network on one picture, and it does very well on it. So now you give it some other picture. Let's say you gave it picture of a house. Right? And you give it to your, I'll represent it like that. Is it okay, guys? If I represent it with a symbol like this, it's clear, meaning is clear, right? I give it there. Guess what you will expect? What will I get? A house. Are we sure? What if I told you that you will get the tiger? You know why? Because all that the machine is in the tiger. So it just learns to produce the tiger. And what it does is, it completely ignores the input, and only G, the G, it doesn't matter what the latent is. It really doesn't matter what the latent is. G has figured out, has memorized the tiger. G is a lot of weights and biases, isn't it? Remember, 20 cross 100, right? 20 cross 784. That is a whole lot of weights and biases, right? Approximately, what is it? 2,000, like 15,000 or 14,000 weights and biases. That's a lot more parameters than 768. Obviously, it can easily, quietly memorize it. And every time, whatever input you give, it ignores it and produces a tiger. Right? So why did this happen? Why do you think it happened? It happened because you asked the machine, you gave it only one reality of the world, tiger. And you penalize it for not producing a tiger. So what will the machine do?
Always produce the
It will always produce the tiger. In other words, it's a classic case of overfitting to the data. Because it has so much flexibility, it can easily go and memorize the data. Now, what I've shown you is, in a very simplified way, a problem that is there inherently with neural networks. Even today, with large language models, we ask this question: to what extent these machines have memorized in their weights and biases the input data, and to what extent it has actually learned, because learning is generalization, right? In the beginning, people said that no, there is no way, because we have given it trillions of tokens, right? There is no way these machines are memorizing. Right? I'm just taking a digression and talking about this, the latest big language models. Till some researchers pointed out that you can systematically extract the training data from the language models. It will regurgitate it to you. But if it can reproduce it faithfully back to you, it means somehow internally it has memorized it in its parametric memory. So that is one thing you have to always be aware of, that in complex neural networks, there is both going on. Two opposite things are going on: memorization and generalization. And the thing is, often it's hard to tell when the machine is learning. You don't know whether it's actually learning to generalize, because learning, you always want it to be through generalization, right? Or whether it's just memorizing. And by the way, if you have all been through colleges, I'm sure that courses you liked, you learned, courses you didn't like, you memorized and passed, right? So a very similar thing happens in these machines. So we just saw this problem of memorization, and the reason is obvious. The data set is so small, the model is so big. Obviously, it will find the cheap way and memorize it.
So
Isn't
Asif, a quick question here, like, is the memorization because of the weights and biases that have been calculated, or is it something else?
No, it's just that there are enough weights and biases there for it to just memorize, because the only data point it's getting is the tiger over and over again. So it will go memorize it. Are we together?
Okay, got it.
That's it.
Can we call this as an input bias? Yeah.
No, you call it overfitting. It has overfitted. So what should you do? Obviously, if you want to do better data compression, so let's try to be a little bit smarter. What we will take is the MNIST data set, right? And what you do, and by the way, now let's be a little bit more sophisticated. See, remember I said that from here, you went straight down to this tiny little thing. But in reality, what you do is, it is always more efficient to go like this, and then to do the reverse of it. Are we together? This is more really. So people often use the word hierarchical autoencoder, right? In which obviously this part is your, or including this part, is your encoder, and this part is your decoder, right? As always. But you do it in a deep layer. Now comes an interesting point. What you do is you give it lots of different data, right? For example, MNIST is, I believe, 50K training and 10K validation data points, right? So 60K. Suppose you ran this data set through it. Now it is a much tougher time to memorize, isn't it? So it will be forced to learn. And what it will learn is a latent representation, right, of the numbers. And it's quite beautiful. If you look at the latent space, and these latent spaces are worth looking at. So let me give you an assignment, guys. Actually, let me see if I can show that to you. It is worth seeing. See, guys, what I'm going to show you is not from an autoencoder. It's from a different thing called a UMAP. Once again, it's from a completely different thing called UMAP, right? But I'll show it to you just to show how do machines understand data. It's a different algorithm, but I'll show it to you again anyway. Let's go here. It is called Projector. And
I had a question on.
Hold on to your question. I'll come to the question, sir. One moment, please. So I'm showing it to you in a different context, but let me first do this. This will take quite some time. Let me take this. It's going through rather slowly on this machine. Okay, I'll take your question.
So if you fed that same MS data to the first encoder decoder, right, which had only one small network layer,
Yeah.
Would it still memorize a tiger because it's now getting multiple data?
Yeah, that is it. So the point is that you need to give it variety of data. So to prevent memorization, this is a basic lesson I was trying to bring. Not just autoencoders, any neural networks, give it lots of varied data.
Then what is the value of adding those intermediate layers? You said that was important too.
That was important because the learning is more efficient. The hidden representation that it learns is better. Remember, I mentioned in the first session itself that why do we see the universal approximator theorem says that one layer is enough. It has to be sufficiently wide. But the lesson from deep learning is that when you stack layers together, and we saw that in the, remember, TensorFlow playground, that when you stack layers together, it learns quickly and efficiently. Right? So in practice, you stack layers together of decreasing size and then again increasing size, opposite, mirror image of that.
So in the hierarchical architecture as well,
Yeah.
if it feels like only one data point,
Oh,
it
then
is
it
going
will
to
still be
memorize.
the same thing. It will still it will memorize the tiger, even faster.
It's
It will
faster
just
memory.
it will more efficiently memorize the tiger. So
I'll ask you
beware
one
that.
question. Sorry I'm from the remote. So the
Yes.
way I understand, at the end of the day, the memorization and generalization is all about, what are the biases and then, what are the weights and biases, right? So in memorization, the weight and biases only represent only in a small set of data. But
No. Stop right there. Weights and biases have nothing to do with data. Remember, weights and biases are the parameters of the model.
I know. So, okay. So I misspoke. So the weight and biases are realized or configured or, updated for only a small set of data training, right? It gets
Right.
updated. And in the case of generalization, it over and over, it verifies the data. So the configuration of the weight and biases represents accuracy of all data, which we are training. So what I'm trying to say, some of us are wondering what is memorization means, what is generalization means. So we still exactly didn't get it. In terms of what's going on inside the machine.
I'll do a sidetrack on it. Let's do one thing. The memorization versus generalization. This is a topic. How about I cover it after we do this? At this moment, how do machines? How do you know a machine is memorized versus generalized? Right.
Okay.
If I can, I'll give you a very short answer right now. See, if it gets the answer right only for the training data and wrong for all other cases, it is memorization.
Yeah.
Right? Very much in human terms. If you have memorized the answer to the 10 most important questions for the exam, then, and let's say one of them showed up in the exam, you got that one right, all others you completely bombed on, right? It means you had memorized the answers. If you got all 10 right, it means that from learning about, learning the subject, you learn to solve problems that you had not seen.
Yeah, I think I get it, and probably others also get it. But what I was wondering, what does it mean internally? What is the
Yeah, I'll explain that. I'll come to that. But that is literally what I'm coming to, Ram. So that's why I'm saying hold your hold on to your thought. So guys, remember, this is not the output of an autoencoder. Let me be very, very clear. Are we together? All I am doing is showing you what does the latent space structure look like. Right? It is a completely different algorithm that's producing this latent space, but because it is very illustrative, I wanted to show you this. So you notice that this is the MNIST digits. How many digits are there? 0 to 9. Are we together? In a good encoder, this is a different way of encoding, a good machine that projects data into low dimensions. Here, what is the dimensionality? 3 dimensions, right? Remember, this is a 3-dimension. And I have taken these pictures, MNIST dataset. What is the dimensionality of the MNIST dataset? 28 by 28 is 784. A 784 dimensional vector, you project down to a 3-dimensional vector in some sense, right? And still you notice that, what is it doing? It has put all the 3s in one place. Do you see this, guys? Right? It has put all the 1s here. It has put all the 8s here. It has put the 5s here, 2s here. You see, it has somehow figured out what these numbers, like these numbers are different. And they have landed in different places of the latent space. Question.
Is there a reason for why there's like a couple that are out of place?
Yeah, so the reason for that is these machines, any one algorithm will try to figure out, and if you go back and look at what the exact 2 was, its shape would be closer to beginning to look like something else. Right? See, when people write 2, they write in all sorts of ways. It may look practically like a 0 sometimes, right? And things like that. So most of these outliers come because these are handwritten digits, and human beings write with a whole variety of styles. Right? So, are we together, guys? Huh? But anyway, I took this to show you what latent spaces look like. The autoencoder that I just showed you, its latent space does not look like this. It's slightly different, but the point is latent spaces have structure. Are we together? They have really good structure. Yeah. Now, I invite you to look at any of your books, any of the textbooks that I've suggested to you. They all show you MNIST, or actually we can just Google it, MNIST autoencoder, MNIST encoder latent representation. There must be images. If you go and look at the images, yeah. So let me take an image that it looks like. The thing is, most of these have already become simple MNIST autoencoder. Yeah. Let's look at this picture. Yeah, look at this. This is a basic autoencoder. Couple of layers coming down to 2 dimensions. Make sense? Right? A very simple layer. Guys, can you immediately spot the code? Look at this code. Does it make sense? What have you done? 1 feed forward layer for activation. Another feed forward layer, activation. Right? Finally down to 2. Right? And the inverse of it. And then you do some visualization and you try to do the outputs, and you can see, let's see in the beginning. Let me just do this. This is a very nice thing actually. So in the beginning, the machine, would it be able to reproduce it when all the weights and biases are randomly initialized? Tell me, guys. No. If you start, it will not be able to, right? So epoch by epoch, see each of these digits, just pick a digit here and see how gradually it begins to emerge. Right? It gets that. So to fix, and it is getting there, I'll just go to the last in the end. It has picked up, there's a gray here. He just mentions that to fix that gray problem, you can do, and by the time you run the final iteration, it gets cleaned out very well. Like 6 becomes 6. Now, this is a very simple autoencoder. You realize that 6 didn't come out as perfect 6. It's a little bit blurred, right? Sort of sensible is because this architecture that we have, or what we have learned so far, is the simplest one. For images, what would have been a better way to implement autoencoder? Feed forward layer or CNN. You could have convolution and deconvolution layers, right? And if you do that, you will get much better results, right? But let's look at this in this simple thing. Look at this picture, guys. Do you see that the zeros are all here, right? The oranges are all here, the greens are all here, and these things are scattered. Now, looking at this, guys, give me a comment. What is right and what isn't right? Yeah. Both of you. could you sit at a place that I can have straight, because this monitor, I mean, the screen prevents me from seeing you. Either move this side or come at the back row. Yeah. But ask your question first.
Isn't this an overlapping?
Yeah, the overlapping region. For example, in the dead center, what is it? Is it a 5? Is it a 4? Is it what? Is it
8.
Yeah, 8. So you're not sure. There are regions of overlap. So that is one problem. What other problems do you see?
Outline
It's ambiguous, very.
Come again?
It's very ambiguous. We don't really know what is the.
No, in the dead center, yeah, there is a lot of overlap. So it is ambiguous. If I didn't tell you the answer, what point it would decode to, right?
There's also a lot of spread, isn't it, Asif?
Say that again.
There's also a lot of spread. Like even if you look at one, it's spread across a very large region.
That is right. It is spread. That is another good thing. See, guys, do you notice that there's a lot of white space? And in the white space, you have no idea what the machine will have, decoder will have no idea what to decode it to, because it has never seen data in that white space, empty space. Guys, pay attention to what I just said. This is an important point.
Yeah.
There is a lot of empty space in this picture. And if a machine learns this representation and you ask it to decode a point from the empty space, it would feel pretty lost.
So is that because we only are looking at it from a two-dimensional perspective, or
Yeah, so that is another aspect. See, guys, we reduce it down to 2 dimensions. 2 dimensions is too little, right? You realize that this is a massive compression, right? So if you take a higher dimensional representation, let's say a 10-dimensional or 20-dimensional representation, right? What will happen is those overlaps will improve.
And the cluster will become condensed.
Cluster, unfortunately, doesn't become condensed.
Oh, okay. Because of the white space. It won't
There
be
is 20 dimensions has even more space for it to spread out in.
No, each cluster
Yeah,
could be like 1 dimension.
1 dimension. So it's a 20-dimensional space, 20 axes.
Okay. Still again.
So just for intuition, think 3 dimensions. If you do it in 3 dimensions, you do realize that the machine can now spread it out, not overlap. It will spread out. So the overlaps will be less. That is true. That improvement will come. But the problem that happens is, do you notice that all of the shapes, like for example, the shape of all the blue dots, the shape of that blue cluster is very different from the shape of the orange cluster. And the shapes could be whatever it wants to be. Right? The shape of the gray cluster is pretty elongated. Guys, do we see that point? Yeah. Because the loss function just said, just try to produce what we give you. Right? That's a limitation that we will address next week. Yeah. It turns out that you can impose a structure. You can force the latent space to be populated in a particular way.
So I'm assuming that, okay, the input numbers or
Yeah.
the input set, data set
Yeah.
is equally distributed.
Yeah, you can assume. That's a good point. See, what you say is that the more formal statement is that you know the distribution of data in the input space. And that distribution, in this particular case, is really well balanced. There's exactly, like I believe, pretty equal numbers of zeros and ones and etc. It's all pretty well balanced, the distribution is. Guys, with these 2 observations, I will now get back to what we are talking about. But let me ask you this question. So when you do this and you produce, you saw in that example, right, that even a simple, humble feed-forward network was able to, as an autoencoder, compress the data and reconstruct it pretty well, right? That's an achievement. That's an amazing achievement. I don't know. Guys, do you realize that's an amazing achievement of this architecture? Right? It has some limitations. Those limitations we can enumerate. For example, it is not perfect reconstruction. not perfect reconstruction. The other one is that latent space is not, like, it's basically latent space distribution is not perfect. Right? Latent space distribution, not perfect. There are overlaps, empty regions. Okay, but now I'll ask you this question. This machine has seen only digits, isn't it? What do you think will happen if I give it a tiger as input? Do you think it will reproduce a tiger? That's right. It will reproduce some shape like this. Something like this. Right? And you have no idea what it is. Why? Because it has never seen a tiger, isn't it? It has no way to look for a tiger. So you would say that a tiger is a outlier. Compared to the digits 0 to 9, if you give it a tiger, what will happen? X prime, the X prime minus X will be huge. And the squared loss will be huge. Does this make sense, guys? Right. And its reconstruction of a tiger will be really very poor. Right. What is a lesson here? Can you turn this thing to your advantage? Think how you would turn this to your advantage.
Limiting the model to just few classifications.
Say that again.
Like, if I want to build a model that only does a number of classifications, I can say that, let's say I want to identify whether it is a pizza or a hot dog, and anything other than pizza or hot dog will have a huge loss. So I can say this is definitely not a pizza or a hot dog.
Good answer. Anyone else would like to say? See, guys, there is a field of machine learning which is called outliers and anomaly detection. Right? So you have regular data that you expect, and then you have anomalous data. So suppose you train a machine on regular data, right? Only on good data, inliner data, not on the outliers, not on anomalies. What is likely to happen when you give it an anomaly? The reconstruction. So this is the word. So let's introduce a term, reconstruction loss. The reconstruction loss will be high, right? So the larger the reconstruction loss, the more you should feel, oh, there's something odd about this picture, right? See, a machine is running, it's getting zeros and ones. Suddenly somebody gives it a tiger. And you will know, because your reconstruction loss will be huge. So we realize another use of autoencoder. What is that? Anomalies and outlier detection. Right? So it is actually a good thing. Make sense? Okay. So let's do a time check. Oh, 7:23. So guys, this is there is more to autoencoders. The basic idea we learned is that, and by the way, you can, if you do for images, it's better to make it out of convolution and deconvolution, transpose convolutions, right? So I made this whole argument using feed forward layers, but it works much better if you use that CLNs. Now, let me introduce you a question. There is a very interesting idea that is beyond just autoencoders. It says this, and observe what it says. It says that when you introduce a bottleneck in information, see, what did we do? Information was belonging to a high dimensional space, N. And we forced it down to a Z, which belonged to a D dimension. D is much smaller than N, right? Smaller than N dimension, right? You created a bottleneck in the data, and then you let it flow through. Whenever you create a bottleneck representation, right, machine is forced to learn. It cannot memorize, just memorize, right? When assuming that you don't just give one tiger and nothing else but a tiger, like you give it lots of data, variety of data. So think about it. When you are in school, all of you, have you gone through the tedium of teacher telling you, okay, you just read this essay, summarize it in 200 words, summarize it in 500 words. Anybody who has not gone through that? Right? So you all go through it. Why do you think you're given that?
Trying to capture the essence.
to capture the essence.
Multiple things. For example, with the primary reason for the educator is to just force you to read that essay. Right. Then, but the purported reason is that you will learn to tell the important things apart from the non-essentials. Right? You will, that process is learning, isn't it? Give you a lot of things, a lot of facts. You have to pay differential importance to different things, and you get the outline, the core of it in place, because that's all you can remember. That's all you can summarize in 500 words. So this is actually called the bottleneck principle. And it goes beyond just autoencoders, but autoencoders certainly use it quite a bit, a bottleneck principle. Right? And there are researchers who believe that ultimately neural networks, the way to ensure that there is good learning, you have to bring in bottlenecks somehow into the system, right? They do. And in fact, they often take the example of the autoencoder to illustrate this point, that you want it to learn, create a bottleneck, and it will learn to tell the important from the unimportant. Right? This is it. Now, I will talk about what if, can you create autoencoders that did not have a bottleneck, but had the opposite of bottleneck, right? So let's go to, so these bottleneck autoencoders are also called undercomplete. Autoencoders, or they always look like this, right? Are we together? The latent representation is of a smaller size, undercomplete. But what if you did something pretty odd? This is input, this is output, right? Let's say that X again belongs to n-dimensional space, X prime belongs to n-dimensional space, but you just said, oh, let's stick in. And then, of course, you can have intermediate layers, doesn't matter. But basically, you telescoped out and then you telescope back in. Right? So now you have, let's say that you started with 784, but then you went to 10K. Who's stopping you? Well, when you do neural architecture, it's up to you. You can blow it up. Why would we not do this? These are called overcomplete. So this doesn't have a bottleneck, isn't it? And you give it to the machine to learn, and do you think the machine will learn? Yeah, you know what it will learn? It will say, you know what? Here, whenever data comes in, just copy it over here and copy it back here. Right? Just do an identity transform to the latent space and then identity transform back to the output. I'll get a perfect zero loss. Do you see that? Isn't it? So what the machine will learn is a trick. It won't really learn a good representation. Does that make sense? Right? And therefore the argument for the bottleneck principle. But how about this? What if we could have the cake and eat it too? What if you could take an overcomplete autoencoder and somehow force it to learn? Can we do that? So there are various tricks to do. And so I'm going to talk about a few tricks for which you can use overcomplete autoencoder, or you could use undercomplete autoencoder, the traditional autoencoder. Both of them work, but quite often people tend to use overcomplete autoencoder. And one of them is what you do is sparse autoencoder. In sparse autoencoder, you stare at this hidden layer, the big fat layer, the latent layer, the main, this guy here, and you impose a constraint, some form of constraint. Right? You can say that, hey, even though it has 10K neurons, right, most of them better be dead. Right? Most of them, if I give it an input, they're not dead always, but for one particular input, only some of them should light up. Are we together? Other ones should be zero. And when you think about it, things like ReLU really help, right? Negative values, they'll be zero. So it's very easy to implement sparse autoencoders if you have zero. So what you do is you take the loss function, which has your usual term, x prime minus x square, right? I will do that. This is your usual loss function. And what you do is you add a penalty, some form of penalty, to make sure that for any given input, only some of the neurons are firing. Right? You can do it by, say, a k sparse. K sparse, what it does is, it says only k of the neurons can fire. Pick your k. For example, you can say only 20 of the neurons can fire. Right? But if that is the case, then why did we not make it like this?
Yeah, exactly.
20.
Yeah.
Why did we? Who is going to answer me that? If I'm just going to say 20 neurons can fire, why am I not making an undercomplete standard autoencoder?
So one way to do is like maybe you can make that k to be learnable thing.
No,
So
let's
I
keep k fixed. I say k is 20. Why?
We can make neurons specialize on certain types of inputs. So we can have different batches of neurons that can learn different things.
Very close, very close. Anyone else? But yes, very, very well thought out. Anyone else? See, guys, I said that 20 neurons can fire. But the caveat, the thing is, I didn't say that exactly the same 20 neurons should fire no matter what the input is. So for different inputs, different 20 neurons can fire.
So you can
Multiple
increase your problem space
or
domain.
Right. It is almost like, imagine. So I'll give you, I'm just cooking up an analogy on the spot. So it might be cheesy, right? So imagine that you have a big restaurant, right? And in the big restaurant, here is a guy, he can cook Chinese. Here is a guy, he can make sambar. Here is a guy, he can make biryani. And here is a guy who can make Italian, and so on and so forth. Right? Some input comes, triggering it. And maybe they are all connoisseurs of the food. Right? Some input comes. And you need to create a latent representation of the food. One understands Italian, one understands this. So would you not, would only a few of those chefs are allowed to speak only if they identify that food? Right? So what will happen? How many hands will go up amongst the chefs? Very few, right? Do you see that?
Asif, isn't this what, again, like, is this similar to the matter of experts?
Please, no, it is not, and let's not bring that here, right? Anand, the idea is similar. Well, okay. Since you brought it up, give me a moment. See, conceptually, what you're saying is right. The neurons are acting as a mixture of experts in some sense. Only some of the right neurons know to fire for every given situation. But when people bring the word mixture of experts into it, it has a very technical meaning, which is different from the conceptual meaning. In a mixture of experts architecture, Anand, you have something called a gating function, a gating circuitry, and it routes the traffic to specific experts, which are pretty independent of the rest of the network. Are we together?
Yeah.
So conceptually, the ideas do have similarity, but when don't, I mean, it is in some sense, but not in the technical sense, because the MOE architecture, as it was, see, MOE architecture came from Geoffrey Hinton, and its basic architecture was there was a gating function and there were a couple of experts. Yeah? And the gating circuitry only decided which of the experts to give it to. So it was the gating function that decided which experts to call. Right? Yeah. And so therein is the subtle difference. Here we are saying, yeah, but see, in this analogy, the way I gave it, it's like that. Think of it like that. But more formally, don't use the word element. That's all I would say. Okay, guys. So now you got the idea, right? That you can have a whole collection of chefs, if each chef was a neuron, but for a given input, only some of the chefs will light up. It's just an analogy, guys. Take it as an analogy. So what you can do is you can actually have an overcomplete, but you can say, I don't allow more than K neurons to fire. Right? And how do I determine the K neurons to fire? What you do is each of the neurons will fire nonetheless. Right? You take the K largest firings, and zero out the rest. Before you send the signal over to the next layer. Are we together? And you force the machine to learn. So at any moment, what will happen is for any given input, it will be forced to learn no more than a k-dimensional representation of the image, of the input. Am I making sense?
Does it have any connection with the dropouts?
No. Guys, I know that you all are bringing in things that you have been reading, dropout, transformers, and all measure. See, these things have a little bit of resonance because all ideas ultimately have overlaps. But when we are trying to understand it, just stay completely focused on what I'm saying. Put everything that you know aside. But all I'm saying is we are forcing no more than K neuron information to propagate. In dropout, it is different. Since you brought up dropout, what you do is you randomly decide to ignore K of the inputs, like 10% of the inputs, 20% of the inputs, P percentage of the inputs. You just randomly decide to drop it, irrespective of their value. Are we doing that? We are not, no? We are not randomly turning off.
Only looking at the zero thing and then like, I mean.
Yeah, we are picking up the top K topmost and zeroing in the rest. Another difference is typically in dropout, a minority of the nodes are switched off, right? Randomly, completely randomly. Whereas here, what you're saying is, in this large network, I'm going to take only 20 or 30 of the neurons will fire. In fact, majority are turned off. Yeah. So see, a lot of these ideas are adjacent to each other, but you have to be aware very precisely what it is doing. So that's why I say that in a way, you'll get it more if you just stick strictly to the way we are moving forward. Yeah. So all we do is K largest firings are kept. Are we understanding this, guys? Right. Next, this is it. Or what you could do, the other way that people do is, another way is that they say all of the firings must be small. I'm not going to suppress any of the, zero out any of the firings, but the sum value, Z, the size of Z itself, right? Each of the firing, like Z1, Z2, Z, let's say that it is a k-dimensional vector, right? I will take the absolute value of all of this, and the sum total of all of this should not, the total firing, the total light coming out of these things should not be too much. So I will add in the loss function a penalty term that is the size of this, right? So let me leave this. So k sparse is 1, and then you can apply either a penalty term, L is equal to this x prime minus x square plus the penalty term Now, the penalty terms are typically, there are two common penalty terms. One is this one. This is called L1 regularization. Right? You're basically saying that all of the value shouldn't blow up. It should be small. Are we together? Guys, are we getting it? And one of the benefits of L1 regularization is, and you have to know this whole theory of regularization, which I haven't taught you. So just take it as a sort of a gospel truth that L1 regularization automatically manages to shut some of these outputs, switch off some of these neurons, right? It's pretty good at doing that based on the penalty factor. Go ahead.
So Asif, so the first strategy was to have the K largest neuron.
K largest findings and zero the rest.
Yeah, and in second strategy, you added all the those neurons, neuron values as a penalty, right?
Right.
Okay.
As the absolute value as a penalty.
Absolute value as a penalty.
Right. This is it. And Prashant, you have taken ML 100 with me. You remember that?
Yeah.
And we talked about the L1 regularization.
Yes. Yes.
Right? Yeah. So that is what it is. You just add that penalty term.
Okay.
And another penalty term that people put besides this is it's a little bit more sophisticated. What you do, and I'm a bit hesitant to mention that because it gets a bit mathematical. I'll mention it for completeness. Don't, if you get a flavor of it or an intuition into it, it's enough. It is called, you enforce that the Z that comes out, right, all the outputs from Z, from all the data points that you get, all the ZIs that get produced, vectors that produce from all the data. So you have this data set, right? Data, all of those images, let's say, right? Whatever. So each one of them will produce its own Z value. Are we right? Z vector. This Z vector in the latent space will have a probability distribution. It will show a probability distribution, isn't it? Like it will show how I'm clumped here, I'm spread there, I'm more likely to be here but not there. Right? This is called a probability distribution, isn't it? So what you do is you take a chosen probability distribution. You say, I want the probability distribution to look like this, reference. And then what you do, the penalty that you do is, if the probability distribution of the latents differs from this, you penalize the difference, penalize. You start penalizing it, right? But see, I won't go into it because we are going to come upon the topic of variational autoencoders. And just gets there. Okay, forget about this whole discussion, right? There is on your course portal, I put a note which was very popular actually when it came to sparse autoencoders. There was a lot of research literature, but one of the very popular set of notes that the researchers used to refer to was from Andrew Ng, from his Stanford course notes. That particular note, because it was so widely circulated, I have put it on your course portal for sparse autoencoders. It's a little bit mathsy, and you will see this sort of notation. So you will see things like KL divergence. What KL divergence is, I'll explain to you next time. Right? A KL divergence is like, I expected this, you got that. I'm not happy. Right? That's the intuition behind KL divergence. Are we together? And therefore, I penalize you.
So, sometime back we discussed regarding neural networks that for the advantage of neural networks over other algorithms is that they are resilient to overfitting and they kind of do their own regularization and stuff like that. But here we are explicitly doing regularization, right?
That is true. See, the statement is nuanced. We do know that very large neural networks, sometimes if you go on training them, they have a way to self-regularize. Having said that, it is also true that, guys, today I'll take some extra time. It is also true that if you give a sufficiently small data set size, there is no way the neural network will not opportunistically just go memorize your data. Right? It can go memorize it later. There is a potential that it will do that. Right? It can go overfit. So whenever you have a neural network, there is a balance between overfitting, memorization, and generalization. This is not just true of neural networks. It's true of every single machine learning algorithm. Right? You want it to generalize and not memorize. Right? That's something to remember. So guys, these are all ways of doing it. This is one architecture, sparse autoencoders. There is another architecture which is important, and I hope you guys are with me. Yeah, it is, and I'll bring it. What should I call that? Actually, before that, let me give you something easier. Denoising autoencoders. Denoising auto and encoders. What the denoising autoencoders are, and you can do that with either undercomplete or overcomplete, but we typically do it with overcomplete autoencoders is, suppose you have a picture. You have a picture of a cat. Right? What you do is, and this is your autoencoder. So don't give the picture of the cat. This is your actual input. Are we together? What you send is actual input plus noise. Let's say Gaussian noise. There's some form of noise. Are we together? You inject a little bit of noise into it. For example. So now what does it look? The picture looks blurry, right? You send it in, but so X prime that comes, you write your loss function though, you still penalize it for not being able to reconstruct the original picture. Guys, so far you learned that the autoencoder should produce input. It should be able to reconstruct the input, isn't it? But you're saying, no, I'm going to be unfair. I'm going to give you a noisy picture, but I want you to produce me the original, which I haven't shown you. And go learn, figure it out. So another way, I suppose, to give you a cheesy analogy would be, have you encountered courses in which professor taught you the easy stuff on a topic and then gave you all the homework and exam on the hard topics? Right? So
all the time.
Yeah, was that?
All the time.
All the time. Right. So it's a little bit like that. Well, I hope I don't do that. Okay. So it's a little bit like that. What you did is you deliberately made the problem harder for the machine, right? And in this particular case, actually, I shouldn't necessarily say it is like that because it could be overcomplete also. It could be this, or it could be this. It doesn't matter. But overcomplete is more common for this. Do you see this, guys? I could do. So these are called denoising autoencoders. Do they work? Actually, they work. They work very beautiful. So we came up with another use case for autoencoders. What is that?
Denoising.
Denoising. They clean up pictures, isn't it? Right? We can do even better. In the noise, we can just put a black spot here. We can take out this part, mask it, and then say, hey, no mask, no missing parts. What happened to the cat's tail? I need the whole of the cat. Right? So it will then learn to fill it in. Right? So you can do that. That's another useful thing you can do. So what can you do? If you have a coffee stain on your picture, it can remove it. Right? Or some pieces of the picture, old photograph is scrubbed out. Right? It will go and fill it in. So now you're seeing the beginnings of generative, very basic generative ability, right? These autoencoders have. There is one more autoencoder that I would like to end today with. It is called contractive auto. And I would just say, by the way, we haven't come to the best of them. We are still in the kindergarten of autoencoders. Right? Next time we'll come to them. Is that disappointing? But isn't it fun that already there are such powerful ones, right? See, autoencoders has become a vast field, and there is no way I can cover it in this course. I mean, let's put it this way. There are thousands of research papers, thousands, and more keep coming all the time, right? How many of you have played with something called diffusion models, stable diffusion or mid-journey or whatever, or DALI? Guess what is one of the core pieces of them? Autoencoders. Right? And we'll come to the generative aspect next time. So I'll just write this box, whatever this box is under complete overcoming, doesn't matter, right? What it does is, so I might as well do, okay, this is your auto. And then I do this, input I give, and then I give X prime. And then I ask for one thing. If I just slightly change the input, right? Example, slightly shift it a little bit, slightly elongate it, slightly darken it, do something to it. Right? Small perturbations. So if X goes to X plus delta, perturbation, small perturbation, I still want to see the same output, but not only see the same output. What I want is the Z that comes out, Z for X. So F of X, Z, the Z that comes out, here, some latent state will come out from the encoder. And what I want is that the same Z should come out for X plus some perturbation. Right? So in other words, this Z prime that would come out for the perturbation, let me just call it, right? This is there, and Z prime should be equal to Z. It should be the same. In other words, the value shouldn't change for small perturbations. The perturbations has to be sufficiently large for it to. So one way to think of it is that you're nicely going on a boat, small waves come, you're still in the boat. A big wave comes, you're upside down in the canoe, for example. Right? Does that make sense? Or well, more the surfing board is like that. Right? So, am I making sense, guys? Right. So these machines, how can they do that? Yeah.
Sorry, how is that different from the noise removal aspect?
Yeah. I'll come to that in a moment. So guys, for this to happen, you would agree that this, if this is encoder is a function, then you would agree that this has to do with the gradient of Z, like basically a gradient of Fx, right? With respect to X, the gradient of, isn't it? So this must be 0, because how can these two quantities, if Z prime is equal to this and Z is equal to Fx, what does it mean? The gradient should tend to 0. It should be very small. Does that make sense, guys? Yeah. The derivative should be very small. And the formal way to say that is the gradient of X with respect to, well, Fx is the Z, right? Z, it's called its magnitude, right? In some sense, it is called the Frobenius norm. Basically, what it means is that every Z component, let's say, is 20 components. Z1 with respect to every component of the input, Xi, Xj, right, should be small, isn't it, guys? Should be small, right? All of these things should be small, right? Squared thing. If you add up all of these over I and j, all of them should add up to a small amount, very small. So this becomes your penalty term. So one of the effects of contractive autoencoder is, as a side benefit, it tends to behave like a sparse. It does show the property of a sparse autoencoder, but in a very more robust way in some sense. So contractive autoencoders are quite a significant contribution because they add stability. They make the latent representations quite stable. Right? How is it different from denoising autoencoders? See, you could say that a picture and its slight noise added should be the same, should lead to the same latent representation and come out as the same. But what you don't know is, will both of them come out noisy or both of them come out clean? They could be the same thing. The contractive autoencoder would be very happy producing the same answer, but which answer? There's always that. Though I must also say that it does behave reasonably well as a denoiser. So it does behave, because if you do this, if you take a contractive autoencoder and you play the same game, x plus delta, and then x plus noise, and then ask it for x, it will end up cleaning it for you. So it is another, think of it as another way to play your denoising game. Right? So they all are interrelated, all of these, and that's about autoencoder. I'll ask you one question, guys. In machine learning, we talk of two kinds of learning, supervised and unsupervised. In supervised learning, you always give an output. You say, here is if this is the input, then this is the label of the ground truth output, isn't it? And you teach a machine to always faithfully come as close as possible to predicting the ground truth. Does that make sense, guys? That is your supervised learning. That is how these machines behave. But in this particular situation, X goes in, and what is the output? What is your Y? Y is X itself. So people people call it self-supervised learning, right? In some literature, though, depends upon who you're talking to, they might call it semi-supervised learning, because they say, you know what, it is, if you look at the fact that there are no labels, it is unsupervised. If you look at the fact that the labels are there, right, then it is supervised. So what do we call it? Semi-supervised, right? So people use different terms. Some people will call it unsupervised, right? You see all of these words there in the literature based on whose book you're reading, right? The terrible thing is, if you go for an interview, now you have to read his lips or the interviewer's lips. What answer does this guy expect, right? But anyway, just always say that, give the complete answer. Say, if the output is the same as the input, we use the output as the label. Therefore, it's self-supervised, but some people call it semi-supervised. Say it like that different people call it by different names.
So why it is called autoencoder? What is the reason for auto?
Because it encodes and decodes itself. It learns to see. It comes from this part. You give the same thing. It learns automatically to encode an information by creating a bottleneck. Yeah. So that's why it's the autoencoder, encoder, and decoder. So guys, this is about encoders. Now, I'll tell you why the way I mentioned the encoders at this particular moment have a bit of a problem. The latent representation, remember I said that you can do vector arithmetic. If I take a point and the encoding of the letter 8 and the encoding of the letter 3, and I take an in-between point, theoretically, I would like to see 8 gradually melt out to 3, right? But if in the latent space you have empty spots, right? And I pick a point there, which happens to be in between there. But then these machines, they actually don't do very well. They don't know how to decode such points. What we need to do is we need to create a framework. And the other thing is that if you look at those images and go back and look at it, sometimes some of the digits, right, you'll notice that they have a rather long oblong distribution. Some of them are more spread out and so forth. So you don't have well-defined structure. So the next thing we will do in the next session is we will say, hey, we are making these machines learn. Why can't we tell it how we want it to learn? We'll say, whatever the input, at the end of it, your distribution in the latent space should look like this. Right? Each of the data, let's say that you're talking about digits, zeros, they should form a nice Gaussian distribution, like a hill. Right? Then they should form a nice cluster. 1 should form a cluster, 8 should form a cluster, and those clusters should all be close to the origin. They shouldn't be spread far out. Because if they are all forming one big dense region, then what can I do? So long as I stay close to the origin, think about it this way. So long as I stay close to the origin, I know that the machine has learned how to decode that point in the latent space back to a number. Is it making sense? Right? Because close to the origin, it will become dense. Keep it dense, keep everything nearby, and make sure that all of the separate classes are well-formed clusters, and there are no gaps in them. If I could force it to do that, then I get a big property. I can be confident in my generative ability. Means I can just see how many points are there close to the origin. Suppose I take a unit distance, 1 unit distance from the origin in any d-dimension space. Let's say 2-dimensional space. How many points exist in a unit circle? Infinite number of points, isn't it? However, I would have trained my machine with only finite number of points. Let's say 50,000, 60,000 points, isn't it? Data points. They would have landed, the machine will learn to land them somewhere. But now what do I have? So long as I have imposed the structure and I'm confident that close to the origin or within that region, every point it can decode into a shape, numerical shape. What do I have then? I have a generative machine, because every point it will decode into a meaningful digit, isn't it? From 0 to 9, it will decode it into a meaningful digit. Am I making sense? And therefore, we are just one tiny step away from creating our first generative AI architecture. We just need to impose a discipline onto the latent space. And that will be our topic for next week. Now, guys, as I would like to end with this, we haven't given you, because we are moving so fast and we have these architectures to cover, I haven't had time to give you assignments on CNN and on autoencoders. Autoencoders is a simple topic. I ask you to do a couple of simple assignments. I'll post to the web. Do this example. I said about the tiger. What if you create an autoencoder that you train with only one image over and over and over again? Right? But take your favorite image. Right? Your favorite image, for example, can be a golden retriever. Right? And you can keep passing it over and over again. Train it. Take your shape of the autoencoder. Right? Pick sufficiently rich latent dimension, let's say 20 or something. Decode it, and then try to pass it a different picture. See what you get. Right? Play with that. Play with play these games. Then after that, do the autoencoder with the MNIST dataset. The codes are all there. PyTorch website has the code. Everything has the code. MNIST is the hello world of this world, of this space. Actually, take Fashion MNIST. MNIST has become. You will try it with MNIST. Try it out with Fashion MNIST. Right? Create a Jupyter notebook in which you see what the input and what the output looks like. I will give you the solution next time we meet, or before that. But can you guys please try this? Try this and try out the denoising autoencoder. Isn't it magic that a machine actually knows or learns to clean your picture out or complete it? So all of these ideas, if you really think about it, all the ideas that we have been covering, mathematically, I hope you realize, they're very simple ideas. Right? This is the, people have often remarked, and Einstein used to remark on the unreasonable effectiveness of mathematics. Right? It's just amazing how, what far-reaching consequences very simple things have, simple mathematics has. And you will see, I hope by now you know that these things have far-reaching consequences. Also think of what other ways can you use autoencoders. I've given you only a few of the uses. Data compression, cleaning. What else did I say?
Anomaly detection.
Anomaly detection. 3 uses. They are not enough. There are many more uses of the autoencoder. Can I invite you to explore the various practical uses of autoencoders? I'm not talking about variational autoencoders and generative stuff. We'll talk about that later. But just of the autoencoders that you have learned so far, what are its uses? So please go and give time to learning about it. I'll take questions now. We are still on record. Any questions before I stop recording?
So we go to that, like the last one, the contrastive. Just a bit the match there. G prime f of x plus delta gradient f of x.
All you say is minimize. So let me put it in words that will minimize the Frobenius Bayes. I hope I don't spell it right. Norm, Frobenius norm of the, it's fancy math actually. When you say it out, the Jacobian. Okay. Minimize this. This is what this is. Okay. But you see, it's common sense, right? The gradients are this. If I want to minimize the size of the
gradient. Understand that, like the G prime equal to f of x plus delta.
See, that is Taylor expansion. In calculus, it's called the Taylor expansion. It's
So
just a Taylor.
Like f of x plus delta.
Yeah, fx plus delta. This is equal to z prime, and therefore is. Let me just leave it like that. Is equal to. You agree?
Okay.
That's that.
Do we have paper reading tomorrow?
Yes. The title of that paper, paradoxically, is the unreasonable ineffectiveness of deeper layers.
That's deep analysis.
Come again?
Yeah, ineffectiveness of what?
Deeper layers of a neural network.
Oh.
It's a very provocative title, but we'll talk about it the next time. Okay, guys, I'm stopping the recording because we're